Hi everyone, welcome to Math Spellbook. I'm your host Peter, and basically we are going to do some physics problems today. Thank you for the follow, YB Shoegazer. I actually wonder what the characters in your name read. I would like to actually be able to pronounce that, actually, because I don't know if that's Chinese or is that Japanese kanji. I can only know the first character, which is death. I mean, if you're in the chat, like maybe you can break down the pronunciation for me. Hey, Fizzbuzz. Mapping reality to you. I don't want to be a morphism. Maybe you can explain to me what that joke is. Oh, okay, you're gonna lurk. Okay, thank you for the lurk, Fizzbuzz. Hopefully, you get whatever work you need done on your end. Hey, Jeff Gross, how's it going? Well, I'll ask you the same question. What's the best part of your day so far? But for me, I think it's basically just getting a workout in and, you know, being able to stream for you guys. That's the best part of my day so far. I did do some physics problems this morning, but I think I did 3 of them. All of them revolving around work, you know, the physics definition of work, which is force times distance. Well, I'm hoping to lurk in this channel while I work on my... No problem. Yeah, if you just want me to be the background noise for you, you know, just, you know, go ahead and work on the thing that you need to work on. You know, that's what the stream is for. You know, I'm just glad that I can be the appropriate productive soundtrack for you. Yes, your math thing is very soothing. Oh, thank you. I really appreciate that. Well, like, the thing of it is that I don't know if you would consider it mathing, but then again, we're just doing physics problems, so we're just breaking things into math, so maybe we're physicsing? I don't know. I don't know. We'll go with whatever suits anyone's definition. Yeah, so we were basically working on all sciences math, yeah. Of course, like, for me, like, when you start working on physics, like, I had to learn this over the weekend, is that, I had to learn to separate the physics part of my brain and the math part of my brain whenever I do these, because I realized that whenever I try to make it so it's like the math will lead me to the physical phenomenon, I would probably get stuff wrong and not understand why I got it wrong until I actually had to think about it and actually, like, you know, talk to ChatGPT and basically say, oh, I don't know why I'm conceptualizing this as like this and this. And then ChatGPT would be like, well, even though the math is there, you have to realize that the math doesn't tell you everything. And, you know, that is also true. Because, like, I think, like, one example is, like, you know, like, work is, like, force times distance. There was a problem I was doing in this book. Actually, I'll zoom in here. Yeah, it's like 2 tugboats pulling this one, which is like 6.6. Let me zoom in a little bit more so you guys can actually see it better. Okay, so it's like 2 tugboats pull a disabled supertanker. Each tug exerts a constant force of 1.80 times 10 to the 6th power newtons. One is 14 degrees west of north and the other is 14 degrees east of north. As they pull the tanker 0.75 kilometers towards the north, what is the total work they do on the supertanker? Now, when I was trying to solve this problem, when I did it, what I thought is that I would add the work done on each boat and then add them together. But it turned out that was 0, and I thought that was weird. So I thought there's got to be something that I'm not thinking about. And then it turns out the way to solve the problem is that you multiply 2 by the force, by the work done on one ship, or one tugboat, I should say. And then that's the work that's done. And I had to look up on ChatGPT, like, why is it that you multiply 2 instead of adding them, like, together? You know, and apparently because they're the same angle but they're heading in the northern direction, that's why you multiply 2 to one of the ships, because they're practically the same type of work done. So I was like, oh, okay, that makes sense. Does that mean I truly understand that the input of that answer? Probably not, but at the same time, it's like it kind of gave me a little bit more clarity. So why do I bring that up? I bring that up because sometimes, like, the physics has a little bit of hidden properties that the math doesn't make it clear. And that's why I basically am stating that. Anyway, let us get into the study session, shall we? And I will turn my model off so it doesn't cause any distractions. So let's do this. Oh, let's do 6.8. Is this still section 1? Yeah, still on just work, so I guess we have to master a little bit about work. Okay, so here we go. 6.8. I would have to use Quizlet to actually look up the answer for this one. Okay, so a loaded grocery cart is rolling across a parking lot in a strong wind. Dang, hopefully no one's car is gonna get scratched. So with you apply a constant force. So we don't have the actual magnitude, but we have the x coordinate and the y coordinate to the cart as it undergoes a displacement. Okay, how much work does the force you apply do on the grocery cart? Okay, so we'll just rewrite the question so that we know exactly what we're answering for this problem. force and we have a distance. So why is this one double dotted though? Is it because we have to do more work involved? Because we actually have to get the magnitudes? Because work is equal to force times distance, and it's a, let's see, a loaded grocery cart is rolling across a parking lot. I'm reading it twice, so I realized that you guys can't see part of the problem. Let me see. Yeah, we'll leave it like that. Okay. Yeah, the problem I'm working on is this one right here, 6.8. So I will reread the problem again for you guys. A loaded grocery cart is rolling across a parking lot in a strong wind. You apply a constant force to the cart as it undergoes a displacement. How much work does the force you apply do on the grocery cart? So we could probably draw this. So let's have a small grocery cart. Doesn't have to be a good drawing of one. Then a wind comes in. And then I'm guessing we're probably running after the cart. And then once we get the cart, and I'm guessing the cart is going in this direction, which is S. You apply a constant force. So I'm guessing with us, this is our force. Oh, I forgot to draw the wheels. So this is us just running to the cart. So we don't need to know the strength of the wind, but we apply a constant force on the cart. So let us just calculate the magnitude of the force first, because I think that's the easiest thing we can do. Yeah, I'll just put the units in there because it's not that much. Just have to shrink this. I always forget to bring out the calculator for you guys. So we'll move the calculator right here so you guys can see it. So we'll do the square root. Actually, I'll drag this up higher a little bit. Oh, no, don't do that. There we go. Okay, 30 squared. Maybe I should put this in parentheses. Then plus negative 40 squared. Oh, no. Wait, what's going on? Okay, that's not right. I don't know why it was doing that. Hopefully it was just only a bug. Okay, now it's working the way I want it to. Oh, so 50 newtons. That's the magnitude of the force that we apply, and I think we should get the magnitude of the displacement of the cart. So oh, hello. Hey, Goofy the Ultimate. You like physics? Awesome. Like, which part of physics do you like? like your name actually, Goofy the Ultimate Astrophysics Shred. Cool. Are you a student, Goofy? Or are you just someone that just loves the subject? Yes, I know, because it didn't show like the bubble and the first chatter. It's just been a while since I've seen you. So I'm trying to remember exactly the things you told me the last time. Because sometimes when I don't see you guys for a while, I forget, like, you know, certain details that you guys have told me. Was it the universe? So the thing of it is that, like, when people say astrophysics to me, I end up wondering, like, is that just astrophysics? You're just saying astrophysics because, like, are you gonna plan to make a transition to cosmology, or is it just like you just want to do astrophysics? Because there are some people that don't want to go into cosmology, and I understand that. For me, like, if I were to say astrophysics, I would say, like, oh, that's just my first step before I get into cosmology. I mean, I find cosmology very interesting, but some people might find it very boring. Oops. Didn't mean to do that. Squared. I know I probably don't have to put this many parentheses, but sometimes, like, the details sometimes get convoluted. Actually, I probably didn't have to do parentheses around the 9. Okay, so the distance, the magnitude of the distance is 6.8. Well, actually, put, like, no, not 6, 8. 8.4. We'll put 8.46 meters. It was cosmology. I mean, like, how far are you into, like, are you in with your astrophysics studies? Like, are you basically, like, studying the math right now, or are you already, like, doing the physics problems involving astrophysics, or what is the update in your astrophysics journey? Doing both? That's good. How's the front on the math side, and how's the front on the physics side? I'm doing the theory. Oh, okay, cool. That's good to know. I'm pretty sure you'll teach me a thing or two, because I'm still on the basics of physics, actually. I've taken a physics course before, but it was, like, online. But at the same time, it wasn't for, like, a degree or certification or anything. It was just me like doing it. But I think the physics course was, like, kind of like, I don't want to say it's easy, but it was like, it was more like it gave me the challenge to actually learn this stuff, but I forgot things like about electricity and some of the minor details of things like work and potential energy and all that stuff. So let's see. So we got the magnitudes of these. So why is this? So I'm trying to wonder, what is it? Because we know work is the force times, the dot product of the force. So is it trying to get us to do, like, just basically the dot product? Because, I mean, I could have just done the magnitudes. I mean, we could do the dot product. Because then work would be in joules. Yeah, it would be in joules, so So then it would be like 30. But I think what the thing that makes this problem challenging is that like I'll reread the problem. So a loaded grocery cart is rolling across a parking lot in a strong wind. You apply a constant force. So I'm guessing we just run to the cart. Like the way the problem describes, we run towards the cart and we grab it and we manage to, like, you know, hold on to it with a force equal to the equation that we get right here, and to the cart as it undergoes a displacement of this equation. Ooh, no, don't do that. Don't do that. This equation. How much work is done? How much work does the force you apply to the onto the grocery cart? So I'm guessing the force is basically we're stopping the grocery cart, or at least like we hold on to it. Previously, I was doing math with physics to try to understand complex unsolved problems better. I mean, yeah, like, you know, like if you know the equal balance of, like, you know, physical thinking and mathematical thinking, and you're able to, like, combine them in a well-balanced way, so you know that the math is telling you some stuff about the physics, while the physics is kind of eludes the math to go into a direction where the physical theory will tell you something. Imagine a frictionless plane where two cubes with the same mass are placed. An immovable wall has on the left-hand side. Why as you increase 2 orders of magnitude on one mass, where the number of collisions equals the digits of pi. Is that a problem you're working on? Or is this just an explanation of what you're, like, doing with the math that you're working on, I'm guessing? I finished understanding. Oh, okay. Interesting. Oh, the problem I'm working on? I don't have time to try to answer it. Actually, I want to reread what you just typed. Imagine a frictionless plane where 2 cubes with the same mass are placed in an immovable wall on the left-hand side. Why, as you increase the orders of magnitude. On a frictionless plane, when I push one to the other, 1 gram of mass, counting the number of collisions is 3. Huh. Oh, I think I've heard of that. Like, I think that's... I remember watching something on 321 Brown's channel about that. Yeah, I thought that was pretty cool. And then, like, eventually they had someone do the actual real live version of that for them, which I thought was pretty interesting. So, oops. So let's do the dot product of these, then plus -40 times 3 meters. Where's there it is. So this over here so we can see everything here. So 30 newtons times negative 9.0 plus negative 40 times negative 3.0. So that equals negative 150 joules. Because we know the work done is the dot product of the force vector times the displacement. So I want to make sure that that's right though. Because, I mean, it doesn't say anything about an angle, but is it from this that we have to actually get an angle? Maybe we have to get an angle from these numbers, actually. Like, we basically have to do, Because the work done is also similar to force times S times the cosine between the two angles. So we're going to have to find what theta is. And theta should be 1 gram to 100 tons collisions and you must really love this problem, actually, Goofy. Previously, I also did a bunch of work on police. Oh, okay. Yeah, actually, like, I didn't realize that when you're working on a pulley problem, if there's like only one rope. But like imagine you have one rope, but two ends are holding two masses that are the same weight. I didn't know you can actually separate basically the tension in the rope, like the tension of the rope from both sides. I didn't know you can just basically use one side of the rope of the pulley if it has the same mass as the tension. Pulleys, levers, torque, for my basic physics. Yeah. So we have to figure out what theta is. I mean, that is if I think it's gonna be a little bit more, because like, why else would they give us this equation here, these equations here? And because we got the magnitude, which is the first part we need. We just need theta for cosine. So now I have to figure out how to get to theta. To get to theta, it has to be the angle between the two vectors. So I have to because we know that inverse tangent is y over x here. So I mean, if we get the same answer, that's okay, because we're practically doing the same thing, but I just want to be sure that we get the correct answer. Because I get a feeling that the reason why it's like double dotted is because they expect you to find theta through this. Ooh, I hate it when I do that. Moments, center of gravity. So, now I'm thinking right now, like I know I should know this. Like, why isn't I'm drawing a blank now? Because now I gotta figure out. I gotta basically figure out what Y and X are. And. I don't know why I'm blanking out. I think it's because I have to do it in between the angles. In between the vectors S and F. So. I mean, I think it would be the magnitudes, right? No, I don't think it would be the magnitudes. Because... No, I don't want to expand to the cross product either. Because I think that would be too much work. Because I remember there's a way to actually figure out the angle. But now I'm like drawing a blank, and I'm like, why am I drawing a blank? It feels like there's something that I feel like I know this, but at the same time I'm like, why is it that I'm not remembering? Currently... Well, I wish you luck on the problems that you're working on, Goofy. Black holes and Schwarzschild's radius. Oh, wow. I can't wait until you get into Kurt's metric. that should be fun. Dang. Like... What is it that I'm missing? It's like literally like in my head, and I'm like, why isn't that it's like not popping up? Because we need Y and X, but the thing of it is that yeah, it's like, I know I should know this, but at the same time my brain is like fizzling out. I'm pretty sure that's what you guys experience when you take a test. It's like, I should know this, but why is it that I'm not remembering it at this crucial time? Come on. It's supposed to be the angle between both the force and the displacement. Let's draw it out, actually. So, let's say the current goes into displacement of S, and then we apply a force to it. And usually the resultant vector of that would be this. That's just my realistic, like, I guess my ability to try to make it look realistic. Like with the vectors anyway. Yeah, why am I blanking out? Because Is it the magnitude of the vectors? No, because then you won't know which one is X and which one's Y. Yeah, like, it's like I know the math, it's just that for some reason I'm not connecting the physical interpretation. Because we're dealing with two vectors here, and the thing of it is that we want to find the vector, I mean the angle in between the vectors. But I don't know how to interpret like y and x as like, you know, parts of two vectors. I bet you if I looked at the answer, I'm gonna be like, oh my god, it was so obvious. Why did I forget that? That's one of the reasons why I'm stubborn to look at the answers, because I'm like, I should know this. I should find the connection in my own brain to actually get there instead of looking at the solution. Because I feel like if I look at the answer, I'm not going to learn anything. Yeah, I can see why this problem is hard, because like now it's making you think about like all the stuff that you kind of learned, and now you're trying to find a way to feed back into what is it that you're trying to find. Which means that the location of the math and the physics interpretation of this is like not solidified in my brain, or at least it's not in the proper place where it should be in my brain. Which means I have to organize my thoughts a bit better. Oh. The way you find an angle for a vector is basically you take its x component and its y component, but this is a vector between two vectors. So now it's making me think of linear algebra, like the projection. Yeah, because it doesn't say an angle in the problem. So we actually have to figure out the angle. But now like now I'm like totally like stuck. I guess I have to look at the answer. I'm pretty sure, like, when you study math or physics, if you can't figure it out, but you feel like it's on the tip of your tongue, the feeling of defeat. Okay, this is problem 6.8, so it's 8. Okay, we got the hint here. I'm not gonna see the whole solution just yet. I'm gonna see what the hints are. Yeah, it's a dot product. Okay, let's take a look here. Oh, so they did get the same answer. Oh, okay. We were just making it harder for ourselves. I thought they wanted us to get the angle and stuff like that. I was actually doing all that extra work for nothing. But then again, like, that also makes the problem a little bit more challenging. And also it makes me think a little bit more. Actually, that's a good question. I should ask ChatGPT. I actually have ChatGPT right here, so that's also part of a little bit of a study right here. So I'll type in ChatGPT, how to find the angle, not angel, angle, between two vectors. So that way we can probably use it for next time, like just in case. Oh, okay, it's the dot product between the two. Actually, if we did that. Yeah, because I was thinking about linear algebra when I was thinking about this. So it's the cosine, so it would be the it would be that, okay, so let's see if it comes out with the same answer, actually. Hey, drop my pen. So let's actually try that. Let's experiment a little bit. Experiment with the math. So, so it's the dot product between them, so it would be negative 150 joules over the magnitudes, which is 50 newtons and 8 meters. So that gives us the angle, and I think we can do that in our calculator. So we'll clear that, and then we'll make it inverse cosine 150 divided by 50 times 8.46. Non-real result. Why is that? Let me see if it comes out the same way on my calculator. Oh, yeah, it does. It comes out the same result. Dang, we can't even experiment on that? Sheesh. Unless they're both going in the same direction, maybe. But then again, that would be 0. Huh. Very peculiar. Oh well. Oh, let's do a problem from the kinetic energy theorem. I mean the work energy theorem. I haven't done that one. Okay, so let's see. Oh, we can do 614. So we just do this right here so you guys can see it at the bottom. let's see. Let's see. Let's bring up our pen here and let's raise this up a little bit. I guess I was making the last problem, like, more hard than it should be. Okay, so we got a book with a mass of 1.5 kilograms. Pretty heavy book. Is sliding across a rough horizontal surface. So does that mean it has friction? At point A, moving at, so we have an initial velocity. So we'll just draw point A, like so. And at point B, it has slowed down, so final velocity is okay. So now we're given the questions here. How much work has how much work was done? How much work was done on the book between A and B, and B if negative joules of work. Hey Famish, how are you doing? What's the best part of your day so far, my friend? Work is done on the book was there a C coordinate? No, I don't see a C coordinate. So I'm guessing they're adding one. It was done from B to C. How fast? Jeez, I don't like it when my letters turn out like very messy like that. Is it moving at point C? We're having multiple parts here. How many parts do we have? Okay, C is the last one. How fast would it be moving at C if positive 7? No, let's not write it there. Oh. Joules of work were done on it from B to C. Chillin', just grinding some algebra. Okay. So there's a C part here, so we'll just add that there. Okay. So, first one, how much work was done for the book? So, work value theorem, difference between kinetic energy. So, if we write this, final minus, oops. I was about to write plus, but I'm like, no, it's the difference between them. Initial, like that. Okay, so we have a mass. We have velocity. We have the final velocity in the. So, how much work was done for the books between? So, we can use this to get the total work done. So, let's see, we'll just write total work. I'm not going to write the numbers in because I feel like we can just do that on the calculator. So let's bring up our trusty calculator, and hopefully our calculator cooperates with us. Half times 1.5, then the final velocity, which is 3.21 squared. Actually, I should put a parentheses around this so it doesn't look too off. What type of algebra are you working on, Famish? Oh, whoops. It should be the other number. Should be this one. Then 5. That's the correct number, right? Yeah, 1.25. Then over here, the initial velocity was 3.21. Then that squared. Oh, it's not plus, it's minus. Luckily I caught that. Minus. I think that looks fine. I just want to double check to make sure that I didn't type anything else wrong. Okay, so enter. We're left with a total work of 6 joules. Okay, so if negative 7.50 joules of work is done on the book from point B to C, polynomials? Oh, okay, that should be fun. How fast is it moving at point C? So I'm guessing since it slows down here, we have to remember. So we know what the work done is in this scenario. So this one is A. So we'll just circle that. Now for B, we know that the work done in this scenario is negative 7.5. I mean 0.75. Negative 7.5. And we know that we just don't have, so we don't have the final velocity here, but we do have the initial one. So now we just have to work around it. So we'll just minus this, or plus this with this, and then we have, now we just have to calculate we just have to move everything. So 2 times this quantity here leaves us with that. Then oh yeah, this is supposed to be final. V final. So V final is the square root of divided by M. Okay. So now I think we can just calculate the numbers now. Alright, so we'll clear that. So it's supposed to be the square root of 2 times negative 0.750 plus and the mass of the book is 1.5 kilograms. And then the initial velocity we had in the original problem was 1.25 squared. Yeah, because we're like typing a lot of numbers, so I'm just trying to make sure we also have to make sure that we have the right amount of parentheses. We have a parenthesis in front of that, okay. Because I don't want to make sure that I give a close parenthesis where it shouldn't be. And then divide that by the mass, which is 1.5. Which leaves us with a velocity of 75 meters per second. Okay, so now we have to figure it out again. So how fast would it be moving at C if it was positive? So if it was positive, can we change it? So this is for B, and then for C, the final velocity would be, we just have to take away this negative right here. Let's see how much of a difference it makes. I forgot to turn all my blue light settings, causing me to be unproductive. I like to turn it off during the night. Oh, interesting. So the sign makes a difference. Okay, I think those. Okay, so let's see if which number is this? Number 14. So I'm going to check to see if those answers are right. And I do know it's break time, so Quizlet. Luckily they have all the even problems in here, so hopefully we got it right, because it seems like everything is correct. 14, so 14A. Yep, 14A we got correct. Nice. So like, what about B? Yep, we got that one correct. Awesome. And this one, 1 point. Yep, we got those right. Awesome, we got those right. Big pat on the back. Big pat on the back. I think it's because whenever I see the dots, I expect it to be much more challenging. And, you know, like, the problem is, like, challenging. At the same time, it's like, sometimes I do make it over challenging because I think, like, oh, it's supposed to be extremely hard. So because we were supposed to have 15 minutes of break time, I think we may limit it down to 10. I like to turn it off during the night. Yeah, because like also like the blue light, like it's not good to have it on your eyes before you go to bed, because sometimes it just ruins like your sleep cycle whenever you look at, like, say the computer or your cell phone before you go to bed. But if you guys are like if this is your first time on the Math Spellbook channel, welcome. I'm Peter, and basically, if you like math, if you like physics, or you just want to stream to basically make yourself feel more productive, like doing art or basically just doing a project that you're doing on the computer, you can put on our stream and just basically let yourself be productive with us on this marvelous place that we have here. I basically just do math because I just basically try to keep myself more productive and like doing the things that I love. Math and physics is just like the thing that I love, and you know, this channel is called Math Spellbook, so it gets me motivated to actually just be productive doing the things that I like on this channel. And if you guys want to give a follow, please give a follow. If you're lurking, you're more than happy to lurk in the chat if you would like, or just on the stream in general. You can also subscribe to my YouTube channel if you wanted to see what we were up to during the beginning parts of the stream, or you have to go early and you just missed the last part of the stream. I will always upload my VODs onto YouTube, so you can always check those out. In addition, you can also check out our Discord server. If you like math and you want to discuss the new discovery you made in math or in physics, or you're having questions like, you know, about quantum mechanics or something like that, you know, like, I'm pretty sure I'll read your question and be like, that is a very great question. Let's do some research on it. It's more like, I look at it as if, like, I don't think of myself as a teacher. I think of myself as sort of like a participating member of your research team to know more about the universe in general. So I think everyone is either better than me or someone, or the people that are just as curious as I am, we're like equals. So like, it's mostly like us like taking away the academic not standard, but the academic like elitism, and we're just basically just having fun. We're just basically like looking at the math, looking at the physics, and wondering, like, you know, what is it telling us? What is it about what is it about the math? What pattern is it telling us? Or in the physics, like, what is the math equations telling us about this physical phenomenon? You know, it's like basically it's just all of us having fun with, like, you know, I guess like things that people would probably just like, math, I don't want to touch that. Physics, I don't want to touch that. You know, just something to keep in mind. And for all of those that did follow, thank you for the follow. Much appreciated. I always appreciate it when you guys give a follow, or when you guys like drop a, like, subscribe to my YouTube channel, because it keeps me motivated to keep going with the math stuff. As well as the physics stuff, actually. Because I think with physics I have to actually push myself a little bit more, because I feel as if I have never taken a formal class on physics except for algebra-based physics. I have not taken calculus-based physics. I did take an online course on algebra and calculus-based physics, but it wasn't a formal class or anything. But I still forgot things like circuits and resistors and transistors and all the stuff involving electromagnetism. I completely forgot. For like things like work and like energy, conservation of energy, torque, and all that stuff, I feel like I remember most of the equations, but I don't remember how these apply to problems and how to apply them to standard phenomenon, and like break down the problems a little bit. So I actually have to like do more problems involving that, because like I think this week I've been revolving around just work and the work energy theorem, but that doesn't mean I know everything about these ideas. So I'm like trying to do more problems to actually best familiarize myself with it. But of course I'm trying not to fixate on the details too much, because I'll probably move on to another topic. Maybe next week I'll probably deal with potential energy and learn more about potential energy. Because I think the work energy theorem is a pretty interesting one, because like, you know, obviously work is like the force times the distance. So basically how much of a force is carried out to a certain distance. So then basically you have to realize there's energy in that, which is really, really interesting. And then there's like an actual theorem that kind of relates the two. And then when it comes to potential energy, I'm actually curious about that, because I remember that the work energy theorem, I think, also applies to potential energy, or it has its own theorem revolved around it. But at the same time, since it's potential, I find it very interesting that when they do it with potential energy, it involves conservative forces, which is something that I don't fully understand yet. But I think it's really, really awesome to actually think about these ideas. But so far we've gotten the problems, like, we've gotten 2 correct problems, which I'm pretty stoked about, because usually for me I would end up getting problems wrong, and I would be like, just like I'll be like, dang, I'm not doing well. But at the same time, like, when you fail, you basically have to like understand where you fell short on in that case. So it's just a good thing to keep in mind. And it also keeps me humble, actually, because, like, even though I love math and physics, like, I also felt like my identity was kind of tied to, like, I love the subjects, but at the same time, just because I love the subject doesn't mean I know everything about them. And, you know, like, I don't want to tie my identity to something like, oh, I'm smart at physics. I want to tie my identity to just loving the subjects. Because, like, when you love a subject, you try your best to actually make to improve in them, even though you know you might fail, like, in certain parts of it, you know. It's just a way for me to reflect and actually, like, basically, like, love the hobby of actually, like, facing problems, even though I know I'm not going to get every single one of them right, and I know I will never get, like, all of them right. Maybe I'll get, like, some of the basic ones right, but at the same time, it's like, am I doing that out of repetition, or am I doing that because I'm thinking clearly about what each step means? And usually it's, like, me doing it as a habit. Okay, we'll disengage the study timer for now. I will be right back, guys. Just give me 1 second. Okay, guys, I'm back. Sorry to keep you guys waiting. Just take a drink of water here. Okay. So we did one with the work energy theorem. Let's see if we can do one on a different section. Varying forces. Oh, here's one involving calculus. Yeah, we haven't. So this is section 6.3. Yeah, we 6.3. So yeah. So why don't we do the one involving calculus? I think that should be fine. So let's disengage my model, and then let's get back into the study timer, and let's go. Okay. So this is, turn on the pen here. So 6.47. Okay, so this one has calculus in it, so we're gonna be exercising our calculus muscles. So a force in the x direction with a magnitude excuse me guys, sorry about that. Oh, very interesting. So basically it has a, let's see, it's newtons and over distance. Huh. And it is applied to, let's see, the mass is a 6 kilogram box that is sitting on the horizontal frictionless surface of a frozen lake. F of x is the only horizontal force on the box. Okay. If the box is initially at rest, so x is 0. Okay, we can write the question. So what is its speed after it has traveled 14 meters? Okay. So this problem is short to read, but at the same time it gives us a lot of detail. So it says with a magnitude. So I'm guessing basically you have to, okay, so the reason why it's over, like, so the force per meter is basically minus that. Okay. Is applied to a 6 kilogram box. Okay. So that is sitting on a horizontal frictionless surface. So if I remember correctly, like, work done, I believe, is the integral of the force dx. And the initial is 0. What is the speed after 14 meters? Okay, so we have to integrate and then we have to figure out what the speed is. Oh, and I'm thinking that they want us to put it into the work so that way we know the actual kinetic energy. Because if it starts at 0, I'm guessing the initial velocity is 0, so... Because it doesn't say anything about, let's see, a force is applied to 6 on a horizontal surface. So I'm guessing it starts moving when it's like, when it actually starts moving. So we don't know what the final velocity is, but we know the mass. So we have the mass here, so I think that's basically what we have to do here in this case. So from 14 to... Okay, so we're given 18 newtons x. Actually, I should have put parentheses around this one. X, then this times this, and then x squared over, and then we do 0 by 14, and that will give us the total work done. So we can do this in our trusty calculator. So I will move this to this side so we can have space. Now we'll bring out our trusty calculator here, and we have 18 newtons times 14.0 minus 0.530. Oh, actually, you know what? We should put another parentheses here. Then multiply that. I'm just very paranoid because, like, I always want to make sure that the calculator calculates exactly what I want. Okay, divided by 2. I want to make sure that we have every single parenthesis correct. Okay. Enter. So okay, yeah, that is the right lineup I want. So this leads to the work of, well, how many figures do we have? 1, 2, 3. So I think we should just leave it at 200. No, 201. 201.1. 200.1. Dang, I'm mixing up like what I'm saying. Okay, so now we have the work. So we have to figure out what the speed is. So we'll just put this in a box, and then now we imply the work energy theorem. So since we assume the initial velocity is 0, so we don't need to write that down. So what we need to do is just basically just move everything. So V final is going to be 2 times, and then the mass, and then square root. Okay. So, I instinctively grabbed the calculator that's with me in real life. So now we'll just have to write this. Let's clear this from the calculator. Let's see, square root of 2 times, we'll just put the answer here. So the 1 parenthesis, yeah, okay. I just want to make sure it's the right syntax. And then the mass is 6.0 kilograms. So the final velocity is 8.17 meters per second. Okay, just want to make sure that we did everything correctly. Everything looks like it's fine. Hopefully I'm right about work being the integral of force, because I think that's what I remember seeing in the textbook. So, and when you think about it, when you apply a force to a distance, and let's say if you're doing a force to distance graph, yeah, I think that should be correct. Because I'm thinking, like, yeah, it could, like, work can be related to the area underneath the curve if you're doing that. So, I mean, visually, it seems like it makes sense. Okay, so it's 6.47. So I think we can look at the back of the book, and this is chapter. Is this chapter 6? I believe it's chapter 6. Yeah, I think it's chapter 6. So, answers to the odd number questions. We can actually just expand this. Chapter 5. Here it is, chapter 6. Okay, so now we gotta look for 47. We got 8.17. And we got 8.17. Nice, we got that one right. Awesome. We're doing pretty well. We're doing pretty well. I'm actually liking that. Let's get back to where we were, because I think we can go to the next section, which is power. Back to questions. Let's go down here, because we were on varying forces. And of course, me solving problems with each section doesn't mean I know every single thing about the section. Of course not. There's going to be problems where I find a lot of challenging aspects to it. Okay, power. So what I remember about power is that it's work over time. So how much work is done over time. So, so let's see. Why don't we do the first one? The first one looks like it's supposed to be a challenging one. Okay, so it's going to be 8.48. Let's see. A crate on a motorized cart starts from rest and moves with a constant eastward acceleration. So A is equal to, a worker assists the cart by pushing on the crate with a force that is eastward and has a magnitude that depends on time according to... Okay, so that's the force applied. Per second. And okay, so now it asks the question, what is the instantaneous power supplied by this force at t equals 5 seconds. Okay, so we're given an acceleration. So it moves from rest. So the initial position is 0. Moves with a constant acceleration of... Okay. A worker assists the cart by pushing... so let's try a picture. So it's a motorized cart. Okay, so it moves with acceleration of 2.8 meters per second squared. And a worker applies a force which is equivalent to this equation. So we're gonna have to do from 0 to 5 seconds. So what is the instantaneous power supplied by this? So the equation we get is basically, I think it's like the difference in work over time. And I think we can double check that in the summaries here. Yep, here we go. And I think this is the instantaneous time. I mean the instantaneous power, which is like, that's what we're looking for. So in that case, we should probably just erase this and write limit T work, and P is also the dot product of force times velocity. Okay. Okay. Now, let's see. So we have an acceleration and we have a force equation. Now, so we can figure out the force, we just don't know the mass. I mean the distance. So we probably have to figure out what the distance is first. So we have to figure out what x final is. So if we just have a constant acceleration and it starts from 0, so that means the thought process we have to take here is that x final is going to be half times the acceleration time t. And we know that t in this case is 5 seconds. So we practically have all the numbers. We just have to apply them. So x final, we can just do it in the calculator. And so we get a half, we get a half times times 2.880 times 5 seconds to the squared, which leaves us with 5 meters. So 35 meters. Okay. So now, what's next? So we'll just put this in a box so we remember. And now, let's take a look. So we got the distance. So now we just have to there's two ways we can do it. We can either use this formula or this formula. I think we should use this formula though. So P is equal to, so now we have to calculate the work done. So now we have to calculate the force, and basically the distance. We'll just put delta x as the distance, because delta x is practically like, you know, from 0 minus 35 meters. And we also have to calculate the force at 5 seconds. Because we're given an equation, so we just here, and the force is 5.4 newtons per second times t. So F, oops. So F at 5 seconds, that would be equal to, let's bring out the calculator again. So we are given 5.4 times 5 seconds, which equals 27 newtons. So we'll just put work done at 5 seconds, just to make it a little bit easier to show that that's the work done at the final part, which is 27 newtons. And now we have to basically do this. Just the difference between the work and the time. Because what we're calculating, if we do it like regularly, like basically just delta W over delta T, then that's the average velocity. I mean the average power, but we need like the instantaneous power. So we're going to have to do it very close to 5, but not touching 5. So what I think we need to do is that we need to take 27 and then divide that by both sides from left and right. So let's do the Hey Zach, how's it going? Actually, you guys, if you're not familiar with Zach's work, aka e to the 2i pi, he is an awesome math streamer as well. If you're interested in infinite series, as well as linear algebra, or just got math questions in general, you're more than happy to go on to Zach's streams and check out his content. Let me make sure I spelled your name correctly, Zach. Yeah, there we go. Zach knows more math than I do, so he is the person you can check out for your math questions. But how you doing, Zach? What's the best part of your day so far, my friend? And he is actually a professional mathematician, so he knows the mathematical world. It's been good? A good day? Cool. That's good. Where were we? Oh yeah, we were calculating the limit. So let's do, I think we will do from the right. So we're gonna have to do 5. 1, 2, 3. Oh, I regret typing that many zeros, because then I have to keep track, because then I'm gonna have to do this with 9s. 1, 2, 3, 4, 5, 6, 9, 12, 1. Okay, it's 12 zeros. So, okay, so it's getting close to 5.4. Okay, so now we gotta do this with 4. And then gotta remember there's 12 zeros, so we're gonna have to write 13 nines. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I hope that's enough. Under some definition of good. No, I feel like you're just a pro like that, Zach. I actually have to like go to your streams to check out your Infinite series, because I want to brush up on Infinite series, because I never actually got to do Power series or Taylor series when I was in Calc 2. 5.4. Okay, so the instantaneous power is 5.4. Very interesting. Very interesting. Oh yeah, and it's watts. Hopefully that's the right answer. Hopefully that's the right answer, because let's take a look at the problem and review it a little bit. So we have acceleration, and I think we did follow the logic correctly. Yeah, we used the acceleration to get the final distance. That looks fine. And then we calculated at 5 seconds. Gave us 27. So it does seem like we did everything right. And it's an even number, so hopefully I did it right. If not, then I'm going to have to do some soul searching. I'm kidding. Maybe I overlooked something. I could overlook something. That's also a possibility. So this is chapter 6, work in kinetic energy. Exercises. I'm actually looking on the answers on Quizlet. That if you're not familiar with it, this is not a sponsor or anything, but I do love Quizlet. Quizlet like gives you like answers to a lot of textbooks. So this one's number 48. So they did it with the velocity. Oh. No, it doesn't look like we got it right. $378 watts. Okay, I did something wrong. So what did I get wrong here? So we did assume that the velocity is 0. That's what we did. Which part did I got wrong here in this case? Because it looks like from here they use the force times the dot product. The force is the dot product of V approach. So we did the math for the force times 5 seconds, right? That gives 27. So let's see. So they use the force and the... I must have done something wrong. Oh, I think I put the wrong numbers in. Because, I forgot to multiply stuff. Now I see what I did wrong. Where did I put my pen? Oh, here it is. I accidentally put the force instead of the work. I didn't calculate the work. That was the thing I did wrong. I think. Okay, so multiply that by the distance. 35 meters. So that turns out to be 945 joules. And now I think we gotta do this all over again. So let's clear that, and it's 545 divided by 5 dot 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Doesn't seem like that's right, because it's supposed to be 370 something. Because the way they did it is that you have to get the final velocity times time. I mean, that makes it much simpler actually. Then the velocity is like equal to like we have 2.8 times, and then it has to be 5 seconds, which is 14, and they make you basically multiply both, so it's like 27. So I actually have to figure out what the difference is between these formulas. Because I thought this would be the instantaneous, let's see, the power, I might have gotten the formulas wrong. Let's see. The power is the time rate doing, the time rate of doing work. The average, yeah, this is the average. The instantaneous power is the limit of the average power as t goes to 0. Oh, maybe we were doing the wrong number. Maybe that's why. Because it says to 0. I was thinking it had to go like to 5 seconds. So let's just retry what we were doing. So let's erase that. So it's 945 divided by, let's do 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. No, that's not right. Okay, so what is the other one for? The rate at which, here we go. When the force acts on a particle moving with velocity v, the instantaneous power, the rate at which the force does work is a scalar product, like the work kinetic energy power. So they're both instantaneous. So when do you use this one and when do you use this one? Let's ask ChatGPT. When do you apply for the equations for instantaneous Actually, it should be a capital P. I don't know why I put a lowercase p. Is equal to F being a force vector and B being a velocity vector. What situations? Which situations to use following equations? Yeah, I've been doing this practically like all week when it came to like doing problems. Like whenever I got a problem wrong, I had to think about like exactly what was the logic, and I would like probably ask ChatGPT like what to do, or like what the logic is behind it. Okay, this definition of instantaneous power, it means power is the rate at which work is done. Using this when you're working with energy or work over time, especially when you're given a total work or energy change and need to get power. Use this when you have a graph of work versus time or data interval. You're deriving power from energy considerations. You're given work done over a time period, and you want to find the instantaneous power at a specific moment by taking the limit. Well, that I understand, but what about this one? This is a more practical and direct formula for instantaneous power. It derives the definition of work. Okay, the derivative of position. But you know the instantaneous force, okay, and the instantaneous velocity. Vectors acting on the object. You're doing a mechanics problem where the force and motion are involved. You're analyzing power delivered by a force at a moment in time. Okay. So you use this one when you know the actual time and the force that is applied at that specific moment. Okay. That's probably why I got it wrong. So I didn't apply the right formula for this one. So this one is only used for when it's like graphing, derived from energy considerations. You are given work done over a period of time. Okay. So you have to have the work over a period of time for this one. Okay. That makes sense. Although, like, sometimes I kind of wonder, like, why is it that some formulas are situational at that point? But I guess it's because, like, you want to be able to follow the graph. So I'm guessing, like, the ones with limits, you are actually given a graph, and this one is just easier to manage. Whilst this one is more like back at the envelope calculation, quick moment type of thing, if you have all the data. I'm not too bent out of shape about that, actually. That was actually a pretty interesting problem. So we had to use this one, so that's why we got it wrong. We have to use this formula. And actually when I think about it, this was actually a much logical approach. Just use this, since we already know the velocity is 0. The initial velocity anyway. Okay, so since we got that problem wrong, we probably can work on another power problem if we can manage to make that work. Let's see. Okay, here it is. Power. Let's see if we can do simple one. And I think like tomorrow we'll probably try to do another topic. Maybe we'll do potential energy tomorrow. Let's see, how many joules of energy? Okay, let's do like this one. It's like something to get me like thinking about power in a different way. Okay, how many joules of energy does a 100-watt light bulb use per hour? How fast would a 70-kilogram person have to run to have that amount of kinetic energy? Okay, so how many joules? So we're given the power, which is 100 watts, and so we have to figure out. So the time here is just basically 1 hour, which is seconds. So now we just have to figure out what work is. So the T, thus, oops. Delta W. So delta W, we are given, bring out the calculator again. So we are given 100 watts times seconds. So the is 300,000 joules. Okay. I mean, that's a lot of energy. How fast would, we're given a mass of a person, which is 70 kilograms. A person has to run to have that amount of kinetic energy. So, work, total work. So I'm guessing we're just having this relationship, meaning we have to do these type of gymnastics here. So the mass we have is 70 kilograms, and the work 37 joules, which means we do the calculation. So 2 times, well, actually we should put this in parentheses too. Divide that by 70 kilograms. Oh, I wanted decimals. I don't want that. I usually like it. Do you want to do it in decibels, or do you want it to do it in this way? I prefer decibels, thank you, especially in this situation. Divided by 70 kilograms. So they would have to run. Wow, that's fast. 100 meters per second. Okay, hopefully we did that right. So what problem number is that? 49. So 100. So I think we'll check this and then we'll probably conclude it for stream today. Number 6, and this one's 49. So okay. This is 49, right? Oh yeah, there was like 2 parts. Yeah, so like how many joules? So we got the joules and they did, they got it like around 100, but that's basically close to what we got. Yeah, it's like we got it right. Yeah, we got that. Yeah. Okay, guys, that was actually a lot of fun. We got like some questions right, and we learned from ones that we got wrong. So I think I'm pretty satisfied with that. That was actually pretty fun to actually engage with those problems. Sometimes it's worth it doing the easy problems. Well, I guess like I say the easy problems, but they're still pretty challenging. Like the reason why I say they're easy is because they have 1 dot there, and usually when they say 1 dot, that's basically the author basically saying, oh, as long as you know the basic topics of the book, then you should be able to figure it out. With the ones with the double dots, I sometimes assume that they're much harder, because you have to think deeper about stuff. I haven't even done like the 3 dot ones, because those ones I think I get scared with, because I'm like, oh dang, I don't know enough for this one. But yeah, I think that will do it for today's stream, guys. We will be back tomorrow. If you're watching this on YouTube, be sure to drop a like and leave a comment down below, and subscribe if you can. For all my viewers on Twitch, I will leave my YouTube link in the chat, as well as a link to the Discord if you would like to join us on Discord, and also on my Uncle Talks channel if you want to watch me play video games, because I play video games there and I talk with you guys as well there. You know, just give them the positive vibes as usual if you need a pick-me-up. And also, like, I have fun talking to you guys there whenever I play some games as well. And if you're watching this on YouTube, all the links will be down in the description down below. So yeah, thank you for joining me today, guys. Hopefully you got some stuff done, and hopefully you got your projects at least a quarter of the way done, or if you're finally finished with the project you've been working on, congratulations, you made it. So thank you for joining me today, guys, and always remember, everyone is precious. You guys are just as precious as everyone else, and I will see you guys in the next stream. So take care, guys. Bye-byes.